back to the workshop. Today, the first talk of this morning will be given by Neves. He will speak about metrics on spheres where all equators are mean.
Okay, so I want to thank the invitation. It's really a pleasure to see so many friends and acquaintances. Okay, so I'll give a bit of a technical talk. I guess this chalk is white. So everything I'll say, this is only on these two. Okay. So everything I'll say is joined with Lucas Ambrozio. And with Fernando Marques. Okay, so I'll start with a historical perspective. Okay, so the problem started with Zoll in 1903. So Zoll was a Hilbert student, and the thing he found was he found a metric on the two-sphere, which is not round, and such that every geodesic is closed and has length 2 pi. Every geodesic is closed with length 2 pi. Okay. And so they look, on Wikipedia there's a picture. It looks roughly something like this. It's a whole parameter family. The one he found looks something like a nut, and now geodesics will be something like this and like that. Like that. Yeah. But they will always be closed, and they'll always have length 2 pi. If you take an ellipsoid, that will not be the case. If you take ellipsoid, you have 3 closed geodesics, but then if you just pick a point and start the geodesic flow, chances are that it will never close. It will just go on and on. But on this surface, on these spheres, it will always close, and it will always have the same length. And then Funk, which was another Hilbert student, in 1913, this was his thesis, he found a following criteria. If we have a one-parameter family of metrics on S2 R Zoll, if R and Zoll means that this is a one-parameter family of metrics with the property that all geodesics are closed, and the length is 2 pi for all the geodesics. And we start on the round sphere. If you have a family of Zoll metrics, then the derivative of the deformation there, of the conformal factor, rho dot, which is d rho dt when t equals 0, this is a knot function. Okay, so let me tell you what the idea is. Okay, so we have, let's do the picture. We have the two-sphere, and this is the round metric, and we have here one geodesic, gamma, and now as the metric changes, this geodesic will change, which is going to be something like this, right? This would be gamma t, which is the geodesic for GT. And then what we know is that the length is 2 pi. So we know that 2 pi equals the integral of gamma t with respect to the length for the metric GT. And so now we take a derivative. And so we get that 0 equals d dt of the derivative. We differentiate with respect to t. And now we use the fact that the metric is conformal. This is d dt of, we get integral of gamma t of e rho t. Now the length element is fixed. And when we differentiate this, then because it's a geodesic at time t equals 0, then we just get this integral. Okay. So we get the criteria that if we integrate this function along every geodesic, we get 0. Okay? And so we want to conclude that if that happens, the function has to be odd. So now I cannot write there, right? I have to go back there?
Yeah, sorry about that.
It's okay, no worries. Okay. So, so because of this criteria, then we have, let me state this slightly differently. So we get an operator which is called the func transform, which is like this. So consider f. This is an operator from the smooth functions on the two-sphere onto smooth functions on the projective space. And the operator is the following. We pick a function f, and we choose a point on RP2, and then what we do is we integrate along the corresponding geodesic. I'll say what this is, the function f, with respect to the L0, where the picture is, here's S2. We pick a point on RP2, which is either a vector or it's antipodal, would be either this or minus this, it doesn't matter. But this selects, there's a unique equator, and this would be gamma V, which is the set of vectors which are orthogonal to V. So this gives a geodesic. So RP2 parameterizes all the geodesics on the two-sphere, and what this map does is you pick a function, you pick a geodesic, and you integrate with respect to that geodesic. And then the condition he got was that if you have a one-parameter family of deformations, which are Zoll, the deformation, the lapse function, this function here, has to lie on the kernel of the func transform. So this is called the func transform. And so we have that the func transform of rho dot has to be equal to 0. Okay? And so what he wants to conclude is that if you have a function whose func transform, or which integrates to 0 along every geodesic, it has to be odd, right? Of course, if it's odd, then the integral will be 0. But now you could have an even function which is positive on one side and negative on some other side. And when you integrate, maybe you could be, it could happen that would be the integral will be 0 along every geodesic. Of course, that will not be the case, but this requires an argument. So then the claim is that the kernel of f are the even functions, are the odd functions. Okay. And so what func did was he computed the kernel of the func transform, which I imagine he called it something else. So let's just do this here. We need to use a bit of, it follows by computing this on the spherical harmonics. So let me just tell you what the fact is. So let's call it h of k. So I'm going to explain why this is true. Let's call it h of k. These are the homogeneous harmonic polynomials on R3 of degree k. Homogeneous harmonic polynomials in R3 of degree k. Then one can see that the func transform preserves this space when restricted to S2. If you restrict these functions to S2, these are of course the eigenfunctions. So we have that f, if we apply to a harmonic polynomial, we get some other harmonic polynomial. And moreover, f also commutes with the action of SO3. And so because of this, because SO3 gives a reducible representation on the L2 functions, then the func transform has to be the identity, not a multiple of the identity on each space. And f invariant under SO3. So this implies that f, if we restrict to the harmonic polynomials, we just get the constant times the identity. Okay, but the constant changes. So for instance, if k is odd, then the harmonic polynomials will be odd. And of course, if you have an odd function, and if you integrate along any geodesic, things cancel out and it will be 0. So where this constant is 0 whenever k is odd. And then I imagine, so the argument I'm doing is it's in Gilman's appendix to a paper that I'll talk about next. But I imagine this is what Funk did. And then what Funk, I imagine, computed was that one can explicitly compute this coefficient ck by trying on a special homogeneous polynomial of degree k. And then we can compute this. And the important thing is that when it's even, is never 0, okay? And so because of this, if you take any function, or if we take an even function, we can decompose into the harmonic polynomials or into the eigenfunctions, but we only get the ones of degree even. And then if we assume that its Funk transform is 0, because this constant is non-zero, it means that the function has to be non-zero. So let me just...
Is that technical assumption that G of tau is pointwise conformal to the original metric? Is that restrictive at all?
No, because I mean we did it. I mean, if you the thing is invariant, so you can always assume that, right? If you have in our paper, I'll talk about that. We do the general case. I imagine that I don't think so. I'll say that. Yeah. Yes, I understand the point here. Yeah. Yes, let me just finish this. Okay. Okay. So then so let me finish this. So if f is even, so I mean if we have f, okay, so to check this amounts to see that if you have an even function, it does not lie on the kernel there. So so let me just write this way. So if f is a function, I can use the decomposition where each function is a harmonic, is an eigenfunction. What was the notation I used? Okay, and then because of this, if this is 0, we get that this is this. But now all the odd terms disappear. So this is just the sum of k of c, 2k, phi, 2k. And so from this, we get that all the even terms have to be 0 because this is non-zero for all k. And this is the same thing as saying that f is odd. Okay, so now let me state Gilman's result. Yeah.
Did you say in words why it is that f of hk lies in hk?
That's a computation. I mean, it's that's a computation. It's okay. Yeah. No. I mean, that's a simple computation. It's okay. Okay, so let me talk about Gilman. So then Gilman, in 73, he solved the correspondent problem. He did the inverse part, which was if we have some odd function on S2, okay? If you have some odd function in S2, then we can find a family of functions which would be of the form t rho dot plus higher order terms in S2, so that this family will be Zoll. For all t very small. Okay. So essentially, Funk he computed the tangents. You look at the space of all Zoll metrics, and he computed the tangent space at the round metric. And then Gilman showed that for every element on the tangent space, you can produce a family of Zolls. Okay, did the inverse problem. So his approach uses the Hamiltonian description of geodesics. So let me just say something. So he uses the description of geodesics as closed periodic orbits to Hamiltonian flow, periodic orbits to a Hamiltonian flow on the cotangent bundle. So what he finds is if he finds at the same time a family of functions and a family of symplectomorphisms from the cotangent bundle to itself, such that this family of symplectomorphisms conjugates between the Hamiltonian, the geodesic flow for the round metric and the geodesic flow for the new metric. And so if two Hamiltonian flows are conjugate, then it means the periodic orbits are sent to the periodic orbits and all they have the same periods, and so the metric has to be Zoll. Okay. So then going on RP2, now there's a nice result of Green. This was 10 years before in 63, which says that on RP2 there are no Zoll metrics. If G is Zoll on RP2, then G is round. Okay. So the shortest way of seeing this, so let me just prove this, it's to rely on two results, one of Weinstein and the other of Pugh's inequality. So if the metric is Zoll, then Weinstein showed that the area has to be the area of the the area of what you'd get for the symmetric metric. Okay, so all Zolls will have the same area. The area of the RP2 for this metric G has to be what you would get for the round metric, which should be 2 pi squared. Okay, but likewise, if they are Zoll, it means that all geodesics will have length pi, and in particular, the systole will have length pi, which is the smallest geodesic, will have length pi, but they all have the same length. So the systole, which is the length of the smallest geodesic, this will also have length pi. And then there's an inequality which says that the systole is bounded in optimal way by the area, and when the equality is achieved, the metric is round. This is Pugh's inequality. It's a systolic inequality, and so this implies that G is round. Okay. Okay. Yes. Okay, so let me talk about the main results. So the first one, called this theorem A, this is Ambrozio, Marques, and myself. And so the first we do the analog of Gilman's theorem for higher dimensions. But before, let me set up a notation. Oh, okay. So let's do like this. So let's call this space Z. This is the space of all Zoll metrics. So let's call this, but of course this is codimension 1. So let me just say, these are all metrics G on Sn. so that we can find a family, RPN family of minimal hyperspheres, of minimal hyperspheres, of minimal hyperspheres. So this is one way to extend the notion of a Zoll metric. Of course, on the round sphere, there are many more minimal surface than geodesics. And so we are not requiring that it's a metric where every minimal surface has the same area as in the round sphere. We just ask that we can find a RPN family, which is the family of the equators, of spheres, that they are minimal for the new metric G. Yes, so that they are minimal for the new metric G, okay? And so the theorem is that, so now let me write here, the theorem is pick an odd function on Sn, then we can find one parameter family, rho t, which is of the form t rho dot plus higher order terms, so that this metric is all in that sense. So we do the equivalent of Gilman's problem. So let me tell you one corollary of this. Okay. One corollary.
Andre, sorry, could you just explain the Z again?
The Z, yeah, sure. So this is the space of all this is a space of all metrics on the N sphere, with the property that for that metric you can find a family. You can find a family of the same, or it's like this. Let me explain it differently. Well, they will have to have the same area because I could normalize it. I mean, I can put that. And so let me, area of sigma v tilde equals the area of the n minus 1 sphere. Okay. But let me, okay. So let me just say it here. So let's say we go to S3 and we look at the minimal spheres. So it's every equator, every intersection with so S3 is contained in R4. If I intersect with the three plane, with any three plane, I get a minimal sphere. Okay. Now I look for a metric on S3, which has a property that I can at the same time deform all the equators so that they will all be minimal with respect to the new metric. And so this will be, I mean, I don't know how to draw this, but it would be like, we deform this one, that one gets deformed that way, that one gets deformed that, and that gets deformed there. The thing that I should have said more carefully here is that the family of all minimal spheres for the round metric in S3, that's parameterized by RP3. So let me say that, because this part is important. So remark. RPN, this is homeomorphic to the set of all equators, all n minus 1 equators in Sn. And the parameterization is the following. We take a point there that's a vector or is an antipodal one. So we take V in RPN. We get, so this would be the N sphere. This would be either V or minus V. And then we look at all points on the sphere which are orthogonal to the vector V. And this gives me an equator. This is the set of points X such that X dot V equals 0. Okay. So all the equators on the N sphere, they are parameterized by n-dimensional projective space. Just like all geodesics on S2, they are parameterized by an RP2. Essentially, you just need to specify where's the center, and then it's just plane orthogonal to that. And so going back to this space, this is the space of metrics, such that we can find a family of minimal spheres parameterized also by an n-dimensional projective space, where they will be all minimal, and if they are all minimal, they will all have the same area, and we normalize it so that the area is always the area of the round one. Did it get better?
Yeah, it did. And in Zoll's case, you said it looked like a nut and you had like an explicit metric. So in this case, do you have something explicit with that?
We don't, yeah, we don't know any, well, we don't, yes, we don't, yes, so we don't know any, but I imagine one could find, we don't know any explicit family roti like in Zoll's case. Okay. Yeah, I get, yeah. But I imagine that one could find them. Imagine, we didn't worry with that, yes.
But if you drop the lower order terms and you just write these conformal metrics, you know what they look like? I don't want an explicit example, but just, modulo.
But, oh, this?
Yeah, what does that look like for an odd function?
Well, it's like this, so the odd function has to be positive and negative. I mean, it has to switch sign, and so where it switches, where it's positive, you have the sphere. Where this is positive, you will increase the area, and when it's negative, you'll pinch it, like this. Yeah. Where, here the function is negative, and here the function is positive, right? But, yeah, we didn't, yeah. I imagine that one could find explicitly rho t, for which this is true, just by solving some ODE. I can imagine that, yeah.
So maybe there's one other question. So when you say parameter of the RPN, it doesn't have to be the one that's given on the...
Yeah, so the parameters, yeah, so this family, so this is just a source of parameters, right? But now this sigma tilde, it's not the equators. There'll be deformation of the equators. So I take this equator. For this case, I'll have to deform the equator a bit. Okay? Yes.
Also, this theorem, thinking about funds theorem, this is like the common.
Yeah, so this is...
With that.
Yeah, so that, so this is the analog of the Gilman theorem. We also have the analog of Funk's theorem. And so, but I will write it after I write this, okay? Okay, yes. Okay, so sorry for this. This was not so clear, but is the theorem clear? Okay. Yeah. Okay, so let me tell you one corollary. So one corollary is that we can find a metric. G is always a metric on the n sphere, such that G is all, meaning is a metric where we have a RPN family of minimal hyperspheres, but G has no isometries. But the isometry group of G is just the identity. So the ones that Zoll found, I think they had a dihedral symmetry. Okay? But these ones, they will have no symmetry at all. So let me just tell what the idea is. Okay. So, how can we make sure that we can find, how do we know that we can pick a conformal factor so that when we look at these metrics, they will have no symmetries at all? Let me do this. So the idea is, let's just pick some function, we call it R, a smooth function on the n sphere, but let's make it orthogonal to the linear functions. The span of x naught to xn. Okay. So the reason why we put this condition is that if we do this, we know that, so this space is also the kernel of the conformal Laplacian. And so if you have a function which is orthogonal to the kernel of the conformal Laplacian, it means that I can find a deformation which will agree where the scalar curvature will be this function up to second order. Okay? So essentially it means that from this, it means that then we can pick rho dot a knot function, so that if we look at these conformal factors given by this theorem, this rho t, this rho matrix, such that the scalar curvature of this matrix given by the theorem is going to be n times n minus 1, the scalar curvature of the round matrix, and then the first term is going to be t times this function we chose, and then higher order terms. Okay, so we can prescribe the second term on the Taylor expansion of the scalar curvature. Okay. And so now what we want to do is what we do is, well, if we have isometries, let's call this, so if ft are isometries for the metric, for this conformal metric, then it has to preserve the scalar curvature, right? Then the scalar curvature, let's call this just GT. The scalar curvature of the metric GT composed of the isometries has to be equal to this, right? And so what we do is we pick a function R which is not fixed, which is not preserved by any isometry of the round sphere except for the identity. And then with that, then we work a bit and we can show that actually for that specific function, this will never be true. So let me say this. Then we pick a function R, we pick R, where if R composed with A equals R, where A is an isometry of the n sphere, then A is the identity. Okay. And so we pick this function which is orthogonal to the kernel, and it's not preserved by any non-trivial isometry. We do the deformations, and then for this particular function, we can show that if this holds, then f will have to be an identity. And then we show that if star holds, then ft will have to be an identity for all t very small. Okay, so this is the basic idea. Okay.
So, is this because you know that all small deformations of the round metric have isometries? There are small deformations with isometries?
No,
So
no,
why does
no.
it matter that A is that it is invariant under both n plus 1?
No, I mean, yeah. So we want to make, yeah. So I mean, I was oversimplifying. So the thing we do is we pick a function R where for t small, if this is true, then for sure this has to be identity. So the way we do is we pick a function R which is Morse, so it only has distinct finite critical points. So we only have 2 critical points, and the values of the critical points are different. And so this means that if this holds, then this has to preserve the critical points. The critical points have to be fixed points for this. And then we also require that R is such that at the critical points, you look at the eigenvalues of the Hessian, and they are all simple. And of course, the isometry will preserve the eigenvalues, and so if they are all simple, and if it's not identity, it means that for one critical point, this isometry has to change a vector v to minus v. And then we also put another condition where we require that at the finitely many critical points we found, that the cubic derivative in the direction of every vector is never 0. and that's inconsistent with the fact that the function is preserved and that the differential of this isometry has to send a vector v to minus v because, I mean, the parity would be minus 1. So, yeah. But in particular, that function we pick has the property that it will not be fixed by any isometry. And so in reality, the argument, so the argument is not the argument is not that uniform isometry like that, yes. Yeah. The argument is the things we do to make sure such a function exists. I mean, in finding the function and proving this, how do you find a function to make sure that it's not preserved by any isometry of the round sphere, right? The work we have in doing this actually also shows this, yes. And so that's right.
Does this work? So you say using a Hilbert?
It should work, yes, it works. It works. It works. And so there's a canonical book about Zoll metrics, is a Berger, from Berger. And there they do that argument when n equals 2, but they don't use scalar curvature. They use they use a different argument. The idea is the same. But they, instead of using scalar curvature, they use displacement between points. But I mean, the idea is the same, yeah. Same idea, this idea. Okay, is this okay? Okay. So now, so let me, okay, yeah. Okay, so, let me show this other result, which is we call this theorem B, which is an analog of the Funk theorem in some way. Let me get some chalk. And so this result is that there exists W, a neighborhood of the smooth functions on RPN, which is the same thing as saying of even functions, of a neighborhood of 0, so that if rho lies in W and this metric is Zoll, but now we have to do Zoll on the projective space. But the definition is the same. Is that we have a RPN family, but instead of being minimal hypersphere, it's just minimal projective planes. I mean, it's the same picture. So we can find the neighborhood of the origin, so that if we take a function there, and this metric is Zoll, then rho has to be identically 0. What this means, this is the analog of Green's theorem. What this means is that RPN has no Zoll matrix on the conformal class of the round metric if the conformal factor is not very big. Okay. So this is one. But the other thing we construct is that on RP3, we find Zoll matrix on RP3 where all the equators are minimal. But of course, they will not be conformal. So let me just say this. So there exists G metric on RP3 so that all equators are minimal, so that all equators are minimal, and G has only finite isometries, and the isometry group of G is finite. So let me say some comments here. So let me answer. Okay, so let me make some comments here. So the first comment is about the question which was asked some minutes ago, and it's like this. If you have a one-parameter family of Zoll metrics, the same argument of Funk will also show that deformation rho naught has to be a knot function. Okay, because the Funk transform also extends to higher dimensions, and the argument of preserving the homogeneous harmonic polynomials, it also goes through, and everything goes through. So if you have a deformation by if you have a family of metrics which are all conformal to the round one, and they are all Zoll, then the derivative of the conformal factor has to be an odd function. Okay. What this result says, this is the analog of Green's theorem, but the local analog. Green's theorem was, if you put a metric which is Zoll on RP2, it has to be the round one. Here we say that, well, if you put a metric on RPN which is Zoll, and if the conformal factor is close to the identity, then the metric is the round one. Okay? But now, it's not, one should not expect to show that on RP3 you cannot put Zoll metrics. The simplest example is what's called the Berger matrix. So these are some highly symmetric metrics you can put on the tree sphere, and they have the property that they are invariant under the antipodal map. And in particular, the equators are also minimal for that metric. But the isometry group of that metric is not finite. And so what we found, what we also found is, we found a metric on RP3, which has the property that all equators, they are minimal. Of course, this metric cannot be conformal to the round one, because this metric is going to be very close to the round one, and if it was conformal to the round one, then we are saying that there should be none. And so we found a metric on RP3 such that where all equators are minimal, but we can also make sure that the isometry group is finite. And so in particular, it's not the Berger, it's some other examples. Okay. Actually, we compute the tangent space. We look at the space of all metrics on the tree sphere with the property that the equators are still minimal for the new metric. Where when I require the metric to be Zoll, I allow for the equators to be deformed. So this is a different space, is the space of metrics where we prescribe that the same set is still minimal. And so we compute the tangent space to that space. It's a finite dimensional space, and then we make sure that there's one of them where the isometry group is finite. Okay?
This is very specific to Marques.
Yeah, I mean, so there's some complicated algebra there. The issue is you can compute the tangent space, but it's related with what Christo said. You want to make sure that you can compute the tangent space, but it's not obvious that if you take two distinct tensors on the tangent space, the correspondent matrix will not be isometric to each other. That there's not some diffeomorphism from S3 to S3, which sends one metric to the other, right? And so that could be a possibility. And so when you compute the tangent space to all metrics where the equators are minimal for RP3, that's actually a 20-dimensional space. The Berger space, it's a one-dimensional space. But then, I mean, you still want to make sure that it could be, it's not going to happen, but it could be that you have this 20-dimensional space because the tensors are different, but they are, when you look at the matrix, then they are all isometric to the Berger, right? And so that's hard to see just from the algebra. And so we have to, look at the precise description of these metrics. So these metrics, they are classified. They are given of a specific form. It's, I think it's called symmetric killing tensors. And then we have to look at the space of all symmetric killing tensors and make sure we find one there where the isometry group will be finite to make sure it's then the algebra, then I mean, it could be, it's not going to happen. We didn't do that case because the algebra is complicated. But I imagine the same results should be true, yeah. So on RPN, the Berger matrix still hold. Now, of course, we have this space. Now, we classify all metrics where all the equators are minimal, it's a finite dimensional space. Could that all these metrics are isometric to the Berger? I don't think it's going to happen. But if you see our paper, you see that, I mean, there's some, it's something you have to worry about. And so the less dimensions you have, it's easier to see that because the more dimensions, just the space gets larger. Yeah, is this okay? Yeah. Okay.
Algebra, do you mean literally it's an algebraic problem?
Well, it becomes, it becomes an algebraic problem, yes. It becomes an algebraic problem, yeah. I mean, you can, So let me just say some words about the proof of the theorem. of the deformation theorem. So let's do theorem A, which was if you take a knot function, then we can integrate, right? Okay. So let me say some words about the proof. So we cannot use Gilman's approach because he relies on the Hamiltonian the description. So that is not available. So we do a different argument. We do like this. So let's recall that sigma v, that is just the this is just the space of all the equators. Okay. Now we consider the space of deformations. So we consider this space X, and this is the space of all pairs X comma V, such that X lies on sigma V. So this is contained on Sn cross Rpn. And if you think a bit, you see that this is some quotient of the unit tangent bundle, because the unit tangent bundle is all pairs sigma v, where sigma dot v equals 0. And of course, here we make a quotient that would identify v with minus v, okay? So this is not relevant. So we take this space. Rho dot, yeah, it has to be an odd function. If you take some odd function on the sphere, then you can find a one parameter family of functions, rho t, which is t rho dot plus higher order term, such that this is all. Yeah, it's okay. Yeah, my bad. Yeah. So this is deformation, and now let's look at this space of functions. So so this is deformation space. This is all functions, all smooth functions on X, with the property that the integral of sigma v of phi v dot xi, this is 0 for all v and all I going from 0 to n, where let's set up notation where phi v, this is the function you get by fixing the second coordinate on phi. Okay, so this space, this is the family of all equators, and so a function there, it's a family of functions where each function is defined on the equator, and each function we denote by phi v, uses notation. And so this is the family of functions. This is the space of family of smooth functions where each function is defined on the equator. And now this space is a family of functions, each one defined on the equator, but now with the extra condition that they are orthogonal to the coordinate functions. This space parameterizes all deformations of the equators. So if we give a map there, then we can consider an equator, I denote this way, and in simplified notation, this is going to be sigma v plus phi v times v, which is the normal vector. So let me explain this. So there's my sigma v. The normal vector to sigma v is this vector v, but I can't just put it there, right? It's the same vector. And now on sigma v, I have this function phi v, which is I take the function phi and I freeze the second component. So I just get a function on the equator, and this function, I look at its graph. This would be sigma v of phi. Okay. This is how we do. Yeah, we have sigma v and then we perturbed. So all possible deformations of all equators is parameterized by functions on this space. And so then what we do is we consider the following map. This is going to be from smooth functions on the n sphere cross all parameterizations of deformations of the equators, and this is going to give back a smooth function on Rpn cross, again, a smooth function there. And so let me say what the space is. So here I take a conformal factor, I take a deformation, and what I do is I compute A, I'll say what this is, A of rho phi, this is going to be a function on RPN, I can say what this is, A of rho phi at V, this is going to be the area of sigma V phi with respect to this new metric. Okay, so that's a function on RPN, right? And here I'm going to get another function, which I denote this way, h per of rho phi, and I'll say what this is. So if h of rho phi, if this is equal to the mean curvature of sigma v phi, okay, then h perp, so this is going to be a function on this space, because for each point there, that gives me a point on the equator, and given a point on the equator, I get a correspondent deformation, and I compute the mean curvature of that vector. And so then that is just the orthogonal projection. And we define this. This is by definition, is we just take this function, the mean curvature, and then we subtract its projection. In L2. And we do this just to make sure that the function we get satisfies this condition. Okay. And now so the thing we show is that so the proposition is that if lambda rho phi equals the area of the n sphere, n minus 1 sphere, 0, then rho phi, then this metric is all. Okay. So what is the idea? Well, if you pick rho phi, where this is 0 and that is 0, I get that the area constant and that the orthogonal projection of the mean curvature is 0. So if rho phi, if this equals omega n minus 1, 0, this implies that the area is constant and the orthogonal projection of rho phi is identically 0. And now one can check that if I take the gradient of this function, this is going to be a vector, and one can check that this vector we get, that's morally, I mean, it's not identical, but for the purpose of the talk, you can take it as identical. It's very, I mean, it differs from what I'll write by a linear map. That the gradient of this vector, that is the tangential projection of the mean curvature on the kernel, which is going to be this. One can check that this gradient, this is going to be the sum when 0 goes from to n of the projection of the mean curvature onto xi times the vector ei, right? So this is going to be a vector on Rn plus 1, and so that's why I put the coordinate vectors. And so, but on the other hand, this function is 0, and so we get that this is 0. And so if this is 0, it means that all components are 0. And so h rho phi, we can write it as the tangential decomposition plus the orthogonal 1. We can write it this way, plus the perp part. And so this term is 0, and from here we get, if this is a constant function, all these terms has to be equal to 0, so this is 0 plus 0, and so this is 0. So what this means is that now, well, what this means is that we found a map for which we can try to prove the theorem using the implicit function theorem. So essentially, we just need to make sure that the inverse image of this point is a manifold with tangent space projects to the space of the odd functions. Okay. So this is, so I'm going to leave this map here because it is important. I'll leave the rest. So now, so the goal would be to apply inverse function theorem to the map lambda. Now, one problem that arises is that you can't quite apply the standard Banach implicit function theorem because the spaces don't work so well. So let's just think in general terms. If we take rho phi, for instance, if rho is C3 and phi is C3 or C4, then this function will have less regularity, right? Because it takes derivatives on phi. But so this function will like in C2. On the other hand, this function will have more regularity. So this function will be more smooth than what you start there with. And so because of this, we couldn't quite make the standard implicit function theorem work, and so we had to use the Nash. We had to use the Nash smooth inverse function theorem. And this puts some complications because to apply the smooth version of the implicit function theorem, you have to show that this map is surjective, not only at the origin, where you can compute everything, but you have to show that it's surjective at any point that would lie on the zero set. Okay? And so essentially, when we do the linearization, we have to be, one part of the linearization will be the Func transform for these new equators, and you have to show that that's surjective, and that turned out to be a non-trivial problem because the map is not even Fredel. And so we had to use, to define the adjoint and then compose that with the adjoint that becomes an elliptic operator. It's only integral operators, not a differential operator, and then you have to use some of the standard theory of elliptic operators. So I'll just stop here. Yeah. Okay.